As we discussed about misfits in the structure, okay, how these misfits cause internal stresses. We studied two examples. One was a misfit bar in attached to a rigid bar AB. Oh, not yeah. So one was a misfit bar. Yeah. So and then we discussed about the temperature stresses in the temperature misfits which are caused due to yeah, it's not exactly misfit. We discussed about internal stresses in truss members due to uniform change in temperature for bars with different coefficient of thermal expansion. So that's what we discussed in last class. So in today's class, I will introduce the concept of stress element through a simple uniaxial loading problem, and then I will derive the stresses on an inclined structure, inclined section. One is the normal stress, and the other one is the shear stress. How to get it for the inclined section, subjected to uniaxial load. We'll discuss about the sign convention for those stresses, and then we'll solve a simple. We'll find out what is the maximum normal stress, what is the maximum shear stress, and then we'll solve a simple example. Then we will go to a topic on multi-axial loading. This is for a stress element in a this is for a stress element, and we'll define the relations between the stresses and the strains using principle of superposition, and then we will obtain a generalized Hooke's law. So we can derive the generalized Hooke's law from the principle of superposition. And then we'll discuss about the concept of dilatation, that is the change in volume per unit volume. And then we'll have this bulk modulus definition, which relates the hydrostatic pressure with the change in volume. So then we'll solve a very simple example basing on these concepts. So first thing we'll do is we'll look at the stresses in inclined section. So before that, we'll look into the stress element. So we have a prismatic bar which is subjected to axial load P, and what we do, this axial load is acting at the centroid of the cross section. This material is area of cross section is uniform. That's why it's called prismatic. It's uniform throughout the length of the bar. Since the action force is acting at the centroid, it will produce a uniform stress distribution across the cut cross section. Okay, so what we do is we cut a cross section normal to the loading axis. Okay, so the loading axis is the x-axis. So we cut a cross section normal to it, and we look at the free body diagram of the left part. So this is the 3D view of the free body diagram. So on the left hand we have the axial force P, and on the right side we have this right face, we have this stress distribution. So this stress distribution is uniform. That's why it is shown by this rectangular parallelepiped, and this stress value sigma x is given as P by the area of cross section of this right face. So this is a 3D view. What we can do is we can look at it from the z-axis. So we will get a 2D view. So this is how the 2D view looks. So this is like the elevation. So what we have here again, this cross section which was rectangular MN is now simply shown by a single by a line MN. So you have to be careful that although this height is coming, this height h is coming here, but the width is not, that is the thickness is not being shown in this figure. But you have to always imagine that when there is this cross section M1, that means that there is a width in the z plane. Okay, so the actual area cross section of this will be the height h times the thickness or the width. Okay, so the area A will be h times width. Now what is shown here is this normal stress is shown, which is sigma x, which is P by A, and also we are showing there is a small element C. Okay, that element C is a very infinitesimally small. Just for and this infinitesimally small element has faces which are oriented along x-axis, y-axis, and g-axis, or we can say the normals to these faces are oriented along x, y, and z plane, z-axis. So we can look at that element. Okay. So we isolate a small part of the material at that point C, and that infinitesimally small element is magnified, and that magnified image is shown here. So here this face, that is the right face, is coinciding with the cross section of the cut cross section. So this is the right face of the element, and we have the left face, top face, bottom face, front face, and the back face. So on the right face we have that uniform stress distribution sigma x is equal to p by a. So to balance it, we need another force on the left face. So that is also sigma x is p by a. So these two will balance out each other, and this element will be in a state of equilibrium. So this is regarding the stress element. And what else we have? Yeah, this is the infinitesimally small stress element. Now what we do is, this is a 3D view, and what we do is we look at this element from this z-axis. Okay, so we will get a 2D view, and this entire face we'll be only seeing this edge now, and this edge, or we will see only this vertical edge. So the vertical edge is being shown here. Vertical edge is being shown here, and this left face will be only seeing the left edge. So the left edge is being shown here. Okay, so this is the 2D representation of this stress element, 3D stress element, and the stresses are sigma x, sigma x. So that sigma x on the right face is shown on the right edge here, and sigma x on the left face is shown as sigma x on the left edge. Okay, so whenever you see this figure, you have to imagine that in the z axis, along the z axis, there is some thickness. So every edge here is actually a face, okay, with the width equal to the width of the stress element. Okay, so the width will be, say, b. So that b is so every edge is actually a face. So we can say that this is a right face, left face, top face, and bottom face. The front face is this one, which, yeah, and the back face is also coinciding with the front face. So now what we'll do is we will look at the stress element on an inclined section. So we cut the cross section at an angle, and so let's say this cross section has a normal. So this normal makes an angle of theta with the x-axis. So once you cut the cross section, again there is a stress distribution on that cut area. This stress distribution is this indicated by this arrows, and this is also again uniform. Why it is uniform? Because the resultant passes through the centroid of this area, the resultant P, and the resultant is equal to P. So as a result, the stress distribution is again uniform. And if you look carefully, this P is making an angle with the inclined plane, because it's along x-axis, and this inclined plane is making an angle with the inclined x-axis. So it is making an angle. So this P can be resolved into two components, one along the normal and one along the along the tangent. So that's what you will do. So one thing you can look at this 3D element through the z-axis, and you get a 2D view, and the 2D representation is shown here. We have this uniform stress distribution. So this line is represented as a PQ. So again, when you see the 2D, this line represents actually a cross-sectional area, and similarly this line OP represents a cross-sectional area. So the cross-sectional area for OP is the top face, and AQ is the bottom face. Similarly, this cross-section is this left face. So that's what so whenever you see the 2D, you have to imagine that. And what we'll do is we'll resolve that this stress distribution by dividing that into one along the normal component and one along the tangential component. So this resultant force is P. So this normal makes an angle of theta with the x-axis. So the n value is obtained as P cos theta, and we have the tangent, that is a V, which acts along down the, which acts down the incline, and that value V is P sine theta. Okay, so this normal will produce a normal stress on this cross section, and this V will produce a shear stress because it's acting tangentially. It will produce a shear stress on this cross sectional area. The normal stress. So normal stress N is P cos theta, and what is the area? So what we have is, we have say the height is H, and this normal is making theta here, so this will be 90 minus theta, and this again will be yeah. So we have the height H here. Okay, so this angle is theta, this angle is 90 minus theta, and that angle with the vertical is theta. So this value will be H by cos theta, and the area of cross section will be HW by cos theta. We know HW is A, so the area of this inclined surface is A by cos theta. So the normal stress on this inclined plane sigma theta is N by A1. So N is P by cos theta, and A1 is A by cos theta. So cos theta will again go to the numerator. So we will have sigma theta is P by A cos square theta. Okay, so A by cos theta will go to the numerator. So we will have P by A cos square theta. And if you look at the tangential stress, so according to the convention, the tangential stress is represented as up the incline. That is a positive sign convention, but the actual force is acting down the incline. So what we do is we show tangential stress up the incline, and we put a minus value here, okay, minus V by A1. Again, A1 is A by cos theta, and V is P sin theta. So we have P minus P sin theta by A by cos theta. So cos theta will go up, and we'll get the tangential stress as minus P by A sin theta cos theta. That means you reverse this arrows in the downward direction and then put a positive value. Both are the same. Or you can say tau theta is acting up the incline with the magnitude of the value of minus P by A sin theta cos theta. So now what we'll do is we'll work with these terms, the normal stress and the tangential stress, and see how they vary with variation in theta. So let's look at the sign convention. I have discussed sign convention earlier. So the sign convention is, for the normal stress, whenever it produces a tensile force, it is taken as positive. So tensile force is produced when it is acting away from the bar. So here we have the cross section here, and the sigma theta is acting away from the member. So this will produce a tensile force, and this orientation is taken as positive. And for shear stress, we have discussed the convention on the, yeah, so this is the expression for sigma theta. And for shear stress, we have taken the convention that for positive phase, it should act in the positive direction. So this is a positive phase, so it is acting in the upward direction. If you have the top phase, it should act along the x-axis. And this is a negative phase. Here the shear stress positive convention will be that this shear stress is acting in the negative direction here. And if you have the bottom phase, which is a negative phase, the shear stress should act in the negative direction. So in that scenario, then that case that will be called positive. Okay, the shear stress is defined as positive when it has on the positive phase, it acts in the positive direction, and on the negative phase, it acts in the negative direction. So this phase and this phase, that is the top phase and this phase, you should act in the, along x-axis and along up the incline, and this phase and this phase, you should act along the negative y-axis and along the negative x-axis. So then the shear stress is positive. So what we had is, since the actual shear stress force is acting down the incline, so tau theta was getting, we are having a negative value here, minus P by A sin theta cos theta, which is minus sigma by x by 2. So what we are doing here is cos square theta is written as 1 plus cos 2 theta by 2, and here tau theta sin theta cos theta is written as 2 sin theta cos theta by 2. 2 sin theta cos theta is sin 2 theta. So this is how we rewrite this expression. Sigma theta is sigma x by 2 plus sigma x by 2 cos 2 theta, and tau theta is minus sigma x by 2 sin 2 theta. So now let's just look at the maximum variation of shear stress and normal stress with change in angle. What is meant by change in angle? It means how this shear stress and normal stress depend on the angle of inclination of the cut section. Okay, or you can say how the shear stress and normal stress vary with the variation of the normal direction with respect to the horizontal. Okay, so here the normal is making an angle theta with the horizontal, that is x-axis. So let's look at that variation. So we have these forms: sigma theta is sigma x by 2, 1 plus cos 2 theta. So here cos 2 theta is a periodic function. And what is the period? It will be 2 pi by 2 theta. So the period is phi, that is 180 degrees. And here sin 2 theta is also again a periodic function. 2 theta is equal to 2 pi, and the periodicity is pi, 2 pi by 2, which is again pi. So let's look at the plots of this. So what we'll have here is sigma x by 2 plus sigma x by 2 cos 2 theta. So if you look at that plot, usually cos function will start like this. Cos function will start from here and it will go like this. But because it's shifted by sigma x by 2, it is moving up, and we have this sigma x by 2 into 1 plus cos 2 theta. So at theta is equal to 0, we have 1 plus 1, 2. So sigma x by 2 into 2, which is sigma x. So we are having the maximum value at theta is 0. And the minimum value will occur at theta is 90 degrees. So sorry, theta is 90 degrees. We'll have cos 180, and 1 minus 1 is 0. So we'll get, that's where we get the minimum value. And what else we're having is, so what does theta is equal to 0 mean? Theta is equal to 0 means this plane is in the vertical direction. Okay. So the normal is acting along the x-axis. So for that case, the maximum stress, normal stress is produced, which is intuitively correct. Yeah, if you cut a cross section in the vertical direction, obviously you get the stress value equal to sigma x. And what will be the shear stress in that scenario? The shear stress is minus sigma x by 2 sine 0. So it is 0. So when you cut a cross section, when you cut that cross section, the shear stress, that is the vertical tangential component, is 0. So that is okay. Now what else we can get is, where does the maximum shear stress occur? So where does this tau theta will be maximized? So which plane? So that plane, if you look carefully here, sine 2 theta. So sine maximum value will occur at pi by 2. So 2 theta is pi by 2, theta is pi by 4. So at 45 degree angle, we will get the maximum shear stress. So that is what is shown here. This is the tau function. So minus tau sine 2 theta, and the periodicity is minus pi by 2 to plus pi by 2. So total periodicity is pi. So this will repeat every pi. So the maximum value is occurring at theta is pi by 4 and theta is minus pi by 4. And that value is sine 2 theta is 1. So you'll get minus sigma x by 2 for theta is pi by 4. And if you put minus pi by 4, you'll get plus sigma x by 2. And that is what we have here at minus pi by 4. So these are the maximum values of occurring for shear stress. And what are the corresponding normal stress for this plane which is inclined at pi by 4? So the corresponding normal stress is given by this term, and that term is also actually equal to sigma x by 2. So if you put theta is pi by 4, so we'll get cos pi by 2. Cos pi by 2 is 0, and we'll have sigma x by 2. Okay, so this is the maximum shear stress and maximum normal stress, and that occurs at maximum shear stress occurs at theta is pi by 4. So what we can do, we can look at the bar one more time and see the stress element at the centroid, okay, or centroid at any part on the cross section. So we have this bar, and we have that axial load. Now we choose a stress element A. So how is the stress element? All the faces, the top, right face, left face, top face, and bottom face, all are such that their normals are along x-axis or along y-axis. Okay. So that is the stress element A. And stress element B is such that these four faces are such that the normals are along 45 degree. This the normal to this normal is along 45 degree. This normal is along 135 degree. It's making 135 degree with the x-axis, and this normal is making minus 45 degree with the x-axis, and this normal is making actually 275 degree with the x-axis. So let's look at this first case where the normals are along either x-axis or y-axis or positive or negative direction. So we have this stress element, and so for this stress element we have sigma theta, which is sigma x, and tau theta is 0. On the top face we'll have sigma x by 2 cos 1 plus cos 2 theta. So theta is what value we get? So on the top face, what is the normal for the top face? It is acting like this and it is making 90 degrees. So theta is actually 5 by 2. So 2 5 will be cos 2 5 will be minus 1, so it will be 0. Okay. So in the upward direction it is 0. So there is no normal stress acting in the upward direction, which is true. And we don't have any shear stress either here or in this directions. But here for this element which is oriented along that plus 45 or minus 45, so this normal is making 45 degrees. So we have here sigma x by 2, and the shear stress, this shear stress value is what is that? It is tau theta is minus sigma x by 2. So we are inverting the arrow, rotating the arrow along down the incline and putting it as sigma x by 2. So this is a shear stress distribution for this element. So sigma x by 2, sigma x by 2, and here sigma x by 2 and sigma x by 2. Yeah, so if you look carefully, this sigma x by 2 will balance out this sigma x by 2, opposite faces, because they're opposite faces, they have to balance out, force equivalence should be there, so these two will balance out, and this sigma x by 2 will balance out this sigma x by 2, and the tau are such that shear stress is such that the net torque is 0. So if you look carefully here, about this point, this will produce a anti-clockwise torque and this will produce a clockwise torque. So this moment produced by these two shear stress about this point will be 0. Or if you take about this point, this will produce a clockwise torque and this will produce anti-clockwise, and both will produce net moment 0. So this is in moment equilibrium and also in force equilibrium. So this shear stress will balance out this shear stress, and this shear stress on this face will balance out this shear stress. So this entire stress element is in perfect equilibrium, both moment equilibrium and force equilibrium. Yeah, so now we'll look at how to use this knowledge and for actual real life. So usually some materials have shear strength lower than the tensile strength. So those materials will fail by shear. So here suppose we have wooden block. Wood is very strong in compression. So when you compress the wood, what is happening is it will not fail in the normal direction, but it is failing at a inclined section. Okay, this angle of inclination is 45 degree with the horizontal surface. Okay, so here the wood is failing by shear because the shear strength sigma x by 2 is exceeding the shear stress sigma x by 2 is exceeding the shear strength. Okay, so that's why it is failing by this 45 degree inclined line. So this kind of failure is also observed in some low carbon steel which are tested under tensile loading. So for this steel, what happens is when you load the material, you can start seeing some bands which are inclined at an angle of 45 degree. These bands represent the show that the material is failing in shear and the shear strength has been reached, and these bands are also known as they're acting at an angle of 45 degrees with the loading axis, and there is some term for these bands. Okay, so these are called as Luder's band or Pyobert's bands. Okay, so this is regarding shear failure. What I will do is I will just do a small demonstration which you can think of sometime later in the class, later in the course we will come back to it again. So what I will show is small demonstration, hopefully it will be useful. Okay, so actually there was a chalk piece with me, and since we are not using blackboard anymore, suppose this is a chalk piece we have, and suppose if we apply a tensile load on this chalk piece. So I applied a tensile load and actually it broke. And if you see the surface is probably very much a normal. It is in the very much like a 90-degree angle. Okay. This means that the stress value in this chalk piece is sigma x, and the tensile strength is being reached. So the tensile strength is equal to the applied stress. The shear stress is in the chalk piece is sigma x by 2. That is the maximum shear stress is sigma x by 2, which is acting at some 45-degree angle. But the tensile shear strength is greater than sigma x by 2. Okay, so this is regarding this chalk piece. And suppose if you take the same chalk piece and if you apply, okay, you apply a twist. If you apply a twist like this, if you twist it, then it is failing in this way. Okay, so if you look carefully, that angle of failure is around 45 degrees. Okay, but if you apply as a torsion, it is failing in this way. So you can think why it fails in this way. Maybe I can supply the answer right now, but you can think of it. So what we know is the tensile strength of chalk piece is sigma x. Shear strength is greater than sigma x by 2. Now when you twist the chalk piece, it is failing at an angle of inclination of 45 degree. So why is it failing at 45 degree? So you can think of the question. Later I will supply the answer in due course of time. So yeah, we'll come back again to the presentation and we'll solve one simple problem. Okay, so let's come back to this. So here the shear bands, the bands are acting at an angle of 45 degree. In metals, it will be different. If you pull the metal, then you will have cup cone failure. And if you apply a torsion, it will be a perfect normal. Okay, the surface will be cut surface will be perfectly normal if you apply a torsion loading. So it will be opposite for metals. Unlike chalk piece, it will be opposite. So metals are ductile and there is certain different. So you can think about this phenomena. We will discuss that in detail later. So we'll go to the next part. That is a simple problem. So here what we have is we have a bar which is subjected to a compressive load, and this is the cut cross section PQ, and this cut cross section, this is the normal. This normal is making an angle of 25 degrees with the x-axis. So what you are asked is what is the area of cross section is given as 1200, and compression value axial load is given as 90 kilonewton. And what you are asked is you are asked to find the stresses acting on this inclined section PQ, and you are also asked to find the complete state of stress for theta is equal to 25 degree and show the stresses on a properly oriented stress element. So first part is straightforward. We can simply use that formula. Sigma theta is sigma x by 2 into 1 plus cos 2 theta, and tau theta is minus sigma x by 2 sin 2 theta. And second part we'll discuss again later. So first thing is we'll find the normal stress sigma x, which is minus p by a. So applied load is 90 kilonewton, area is 1200. So we'll have minus 90 kilonewton by 1200. So this kilonewton we write as into 10 power 3 newton. So 90 into 10 power 3 by 1200. We will get newton per millimeter square, which is also megapascal. So we'll have minus 75 megapascal. Now you can look at the stress. Look at the stress element here. So this surface, this is actually a surface. We are looking at the 2D view. So this edge is actually a surface, and this normal to the surface is like this, and it is making an angle of 25 degree with the horizontal. And here this normal is like this, and this is making an angle of 135 degree with the horizontal. So yeah, at 25 degree. So for this surface, what is tau theta, what is sigma theta, and what is tau theta? So we apply that formula. Sigma theta is sigma x cos square theta, or sigma x by 2 1 plus cos 2 theta. So sigma x is negative value minus 75 megapascal and cos square 25. So you are getting minus 61.6. So tau sigma theta is acting is minus 61.6 acting away. So what we will do is we reverse the arrow and remove the negative sign. Okay, and similarly tau theta we are getting minus sigma x cos theta sin theta. So minus and minus 75 will become positive. So we are getting around 28.7. So the tau theta is acting like this. So what we are doing is we are reversing the arrow and removing that negative sign. So this is the compressive force, compressive stress 61.6, and tau theta on this phase is acting in the positive way. So it is 28.7. Okay. Now what we'll do is we'll calculate the stress on this phase. Okay. This is looks like a edge, but it is actually a phase. So first we'll draw a normal here and see what angle it is making. So the normal makes an angle of 115 degrees. So theta will be 115 for this phase. Okay, so we'll apply again the same formula. Sigma theta is sigma x cos square theta. And we get minus 75 megapascal. Cos square is cos square 115. We are getting minus 13.4. And tau theta is minus sigma x cos theta sin theta. So minus or minus 75 will become positive, and you're getting 28.7 megapascal. So tau theta, this is a positive phase and we are getting a positive value. So this 28.7 will act in this direction, and sigma theta is minus 13.4. So it is sigma theta in this direction away from the element with a negative value. So what we will do is turn the arrow and remove the negative sign. So we are getting 13.4 normal stress and 28.7 shear stress. So if you look, the shear stresses on this phase and this phase are acting towards each other, and this is a positive value, this is also a positive value. This is a right phase which is positive phase and is acting in the positive direction, and this is the top phase, again positive phase is acting in the positive direction. Now we can do a similar analysis for this phase. So the normal to this phase will be, it is 115 plus 90. 115 plus 90 is 205, and we can get these values here. And for this phase it will be 275 or minus 25. So you can put theta is minus 25 and get the stresses here. So you can apply the formula and get the answers. You'll get what you can do it in another way also. So the second way to do that without using the formula is, so we have here on this phase a compressive stress 61.6. So to balance it, a compressive force will act, equal and opposite compressive force should act here. So that value is again minus 16.6. So this is another way to get the stress values. And similarly on this phase we have a compressive stress 13.4. So to balance it, another compressive force will act in this direction. So that is 13.4. And the shear stress, how should it act? So here it is tau. So to balance that shear stress, on this phase the shear stress should act in the downward direction, and that value is 28.7. So this shear stress is balanced by this shear stress on this phase. Similarly here the shear stress is acting 28.7 on this, like this, in this direction, and to balance it we need 28.7 acting in this direction. So we have the complete stresses, complete state of stress. So sigma x, sigma y, tau xy. Okay, that's another way to represent it. We'll discuss that again later classes. So with this we conclude the description of the state of stress for an inclined section. Okay, so we will I'll take a break and then we will start another set of slides. So we'll start that new set of another topic, which is the multi-axial loading and the derivation of generalized Hooke's law. Okay, so what is multi-axial loading? So in the previous example, what you have seen was a bar which was subjected to a uniaxial loading. That is, stress is acting only along x-axis. And the stress element, if you see, that there was only sigma x acting there, and there was no stresses along in the y direction or in the z direction. In real cases, we can have cases where stresses act along x-axis, along y-axis, and z-axis. So those scenarios are called multi-axial loading cases, and we have that stress element shown. We have this stress element here. So we have stress sigma x along x-axis. So to balance it, an equal opposite sigma x will act on the opposite face, and sigma y along the top face, and to balance it, a sigma y acts on the bottom face, and sigma z on the front face, and to balance it, a sigma z on the opposite face. Okay, so these are the normal stresses which are acting on these faces, and there is no shear stress shown here. There is no shear stress acting on this any of these faces. So this is a multi-axial loading scenario, and what are we interested in? We are interested in what are the deformations produced in this stress element under the action of these normal stresses. So how do you calculate these deformations? So we'll use the principle of superposition, but before that, we'll look at that actual deformations. So let's take this stress element with initial length 1, that is width along the z direction, width along the x direction, y direction, and width along the x direction. So all these are equal. So this is a cube with side length 1. Now under the action of load sigma x, sigma y, and sigma z, this cube is stretching by certain amount. So let's say the strains, corresponding strains along x, along y, and along z are epsilon x, epsilon y, and epsilon z. So what will be the length of the deformed cube? So this length is along initially 1, and under the due to strain, the elongation will be 1 times epsilon x. So the strain elongation will be epsilon x. So the total length will become 1 plus epsilon x. So this length is now 1 plus epsilon x. And similarly along y, the initial length is 1. So we multiply by epsilon y to get the elongation. So epsilon y is the deformation, is elongation, and total length will be 1 plus epsilon y. And similarly, this length along z will be 1 plus epsilon z. So this is the deformed stress element. And what we do is how to relate this deformations with the strain components. Okay, how to relate the stress components with the strain components. So we'll apply the principle of superposition. So in this principle, what we do is we apply each stress separately. So first we'll apply sigma x and find what is the deformation. Then we apply sigma y and find what is the deformation or the strains. And then we apply sigma z and then find what are the strains. Then we add all those deformations and get the final answer. Okay, so to apply the principle of superposition, the first thing is we should be working with a linear elastic material. Okay, so the applied load will produce a equally proportional effect. So if you apply twice the load, the deformation will be twice the initial deformation. Or if you reduce the load by half, the deformation should also be reduced by half. So that linearity should be present. And the second thing is the deformations are very small. As a result, suppose if you apply sigma x, the lengths are very the increase in length is very small. So we can add up all the total effects. If the geometry itself is changing by large amount, then then we cannot apply the principle of superposition. because when the actual lengths change, the geometry is changing very drastically, then yeah, we cannot apply this principle of superposition. We have to use advanced techniques. So let's apply the principle of superposition now. So yeah, first thing we'll do is we apply stress in the apply only the sigma x stress. So this is our initial cube with side length 1 1 1, and we are applying sigma x. So under the action of sigma x, the length 1 will deform and it will become epsilon x. So that epsilon x is given as, that is a normal strain, is given as sigma x by E. And what will happen is this body will shrink along y direction and also along z direction. Okay, because it is expanding in the x direction, there will be some shrinking in the y direction and in the z direction. The shrinking we can that is the lateral strain, and that lateral strain we can get from the Poisson's ratio. So the lateral strain in the y direction epsilon y is minus nu times epsilon x, and epsilon x is sigma x by E. So the lateral strain is minus nu sigma x by E. Similarly, lateral strain in the y direction is minus nu epsilon x, which is minus nu sigma x by E. So this is under the application of load in the x direction. Now we apply load in the y direction. So we'll have the normal strain in the y direction epsilon y, which is, sorry, this is actually sigma y. Okay, this is sigma, this is actually sigma y. Yeah. So epsilon y is sigma y by E, and we'll have compression, we'll have shrinking in the x direction and shrinking in the z direction. Okay, these two directions there will be shrinking taking place, and that corresponding lateral strains are minus nu sigma y by E and minus nu sigma y by E. And we are applying now load in the z direction. So there will be normal strains produced, which is sigma z by E, and there is shrinking in the remaining two directions, minus sigma z by E and minus sigma z by nu sigma z by E, that is in the x and y directions. Now if all the three loads act together, three loads, sigma x, sigma y, sigma z, what will happen? So what we will do is, so all the three loads are acting, so we know the strains produced by each stress. So in the x direction, it is sigma x by E, here it is minus nu sigma y by E, and this is minus nu sigma z by E. So if all the loads are acting simultaneously, the strain in the x direction will be sum of this value plus this value plus this value. Similarly, if all the loads are acting in the y direction, so the strains will be sum of epsilon y minus nu sigma y by E, sigma y by E, and again minus nu sigma z by E. So that's what we have here. Epsilon x is sigma x by E minus nu sigma y by E minus nu sigma z by E. So this is the sum, and that is the resultant strain produced due to the action of these three stresses simultaneously, sigma x, sigma y, and sigma z. Okay, sigma x is due to the normal strain, and sigma y, this component, is due to the lateral contraction. So that is shown by the negative value here. And minus nu sigma z by E is the lateral contraction due to the application of sigma g stress. Okay, so this is for stress in the x direction. Similarly, due to stress, this is the strain in the x direction, and similarly strain in the y direction we can get directly sigma y by E minus nu sigma x by E minus nu sigma z by E, and similarly sigma epsilon z is sigma z by E minus nu sigma x by E minus nu sigma y by E. So these relations are also called as generalized Hooke's law for multi-axial loading case for a homogeneous isotropic material. So when you are using Poisson ratio nu and Young's modulus C, there are only two terms, and isotropic materials can be characterized by these two terms, E and nu. And if the material is orthotropic and all, we need additional constants. So we will not discuss that. So this is a generalized Hooke's law. For the uniaxial loading case, what happens is sigma y and sigma z are 0. So we get our simple Hooke's law, epsilon x is equal to sigma x by E. And yeah, so we can neglect these two terms and we can get the epsilon x. And epsilon y, also we can neglect epsilon sigma y and sigma z, which are 0. We'll still have the lateral strains coming here. So minus nu sigma x by E. And epsilon z also, we have minus nu sigma x by E. So this is one of the problem in the homework in the given module. So where you are asked to find the lateral strain and decrease in the diameter of the bar, which is for a uniaxial loading problem. We have the generalized Hooke's law, and then what we can do is we can calculate the change in volume of the stress element. So we have this initial stress element with which is a cube with side length 1, and under the action of the loads, the deformation is 1 plus epsilon x, 1 plus epsilon y, and 1 plus epsilon z. So the total volume will be multiplying all these three values. So 1 plus final volume 1 plus epsilon x, 1 plus epsilon y, 1 plus epsilon g. So there are 2 into 2 will get 4 terms, and then 4 into 2 you will get 8 terms. So the 8 terms are here: 1 plus epsilon x plus epsilon y plus epsilon z, and epsilon x, epsilon y, epsilon z, epsilon x plus epsilon x, epsilon y, epsilon z. So we have 1, 2, 3, 4, 5, 6, 7, 8 terms. So out of these 8 terms, these terms where you are multiplying epsilon x and epsilon y, these can be neglected because strain values are usually very small. That's like 10 power minus 3, 10 power minus 4. So you are multiplying with again 10 power minus 3 minus 4, it will become 10 power minus 8. So we can neglect these terms when you compare to these single terms, first row terms. And similarly, epsilon x, epsilon y, epsilon z can be neglected. So we will get the change in volume as means final volume and initial volume as 1 plus epsilon x, epsilon y plus epsilon z. Okay. So yeah, so this cube has initial volume 1, and the increase in volume for this cube is epsilon x plus epsilon y plus epsilon g. Suppose if the cube has length a, b, and c, what will be its increase in volume? So can anyone answer this? So initial length is a, and height is b, width is c. What will be the change in volume? So for that case, if a, b, c is the initial volume, this change in volume will be a, b, c into epsilon x plus epsilon y plus epsilon g. You can do it. Actually, this is g. Okay, so what you do there is you will have a plus a epsilon x, b plus b epsilon y, c plus c epsilon z. So we can take a terms common. So you'll get abc into 1 plus epsilon x plus epsilon y plus epsilon g, and here you will have abc. So if you subtract, you will get abc into epsilon x plus epsilon y epsilon z. Okay. So if the initial volume of the cube is abc, then the change in volume will be abc into some of these three terms. So now we will introduce a term called dilatation, that is defined as change in volume by initial volume. So change in volume by initial volume is this term, epsilon x plus epsilon y plus epsilon g, and that is also denoted by this letter E. This letter E is called the dilatation. Okay. You can call it as define it as change in volume per unit volume. Okay. So per unit volume is, it refers to the initial volume. So we can derive the expression for E in terms of the stresses. So what we do is we replace we can use a generalized Hooke's law. So we have sigma x minus nu sigma y plus sigma z by E. So that term, so again sigma y, epsilon y is sigma y minus nu sigma x plus sigma z by E, and epsilon z is sigma z minus nu sigma x plus sigma y by E. So we are having this sigma y, nu sigma y, sigma x, sigma y repeated twice. So we'll have this minus 2 nu terms, and here the normal terms sigma x plus sigma y, sigma z. So we can take sigma x plus sigma y plus sigma z common, take it out, and then we'll get 1 minus 2 nu by E. So this is the expression for dilatation for this multi-axial loading scenario. So the dilatation is equal to 1 minus 2 nu by E, sum of that stress components, normal stress components. Now we'll look at a special case which is of hydrostatic pressure. So what is hydrostatic pressure? Suppose you are swimming in a pool. So what you can see is you can experience pressure of water acting throughout your body. It will produce a compressive stress on your body. Okay, so this pressure, hydrostatic pressure, if you take at a given depth, it is uniform. So we take a small point, a rectangular stress element within this water body, and that rectangular stress element is shown here in the magnified way, and the hydrostatic pressure will be acting equally in all the three axes, along all the three axes. So it will be p value, and p value. So it is shown in the acting towards the face, so that means it's a compressive stress. So we have sigma x is minus p, sigma y is minus p, and sigma z is minus p. So we can apply the dilatation relation. So E value will be 1 minus 2 nu by E, minus p, minus p, minus p. So we'll have minus 3p. And what we can do, we can have p by minus p by E term here on the left hand side, and E by 3 of 1 minus 2 nu term on the right hand side. So this is the hydrostatic pressure, and this is the dilatation. The ratio of the hydrostatic pressure to the dilatation is a constant, and that constant is known as bulk modulus, or there is another term for it. It's called the modulus of compression. Okay, so it's like if you say F by delta or P by delta is equal to K. So this is like a stiffness term. Bulk modulus, like it's like a stiffness term. So higher is the bulk modulus. What will happen? Lower is the dilatation. Okay, so that's what you can say. So E is equal to minus P by K. So when you have a high bulk modulus, the dilatation, that is the change in volume, will be less. And if the bulk modulus is less, then this value will rise up, and the change in dilatation will be high. Okay, so the expression for K, that is, we define that quantity K, the bulk modulus, as E by 3 of 1 minus 2 nu. So now if you look carefully, any body which is stable, unless it is a bomb, okay, if you think of a bomb, if you apply compressive force on the bomb, then it will blast, and there is an increase in volume. So that is an unstable material. But most materials are stable. So if you have a sponge, if you squeeze it, it will reduce in volume. So most materials are stable, and under hydrostatic pressure, the change in volume is negative. So change in volume is negative means the E value is less than 0. So since hydrostatic pressure is minus P and E is less than 0, this term will be positive. Okay, so K term is a positive quantity for stable materials. So E by 3 of 1 minus 2 nu, which is greater than 0. That means 1 minus 2 nu is greater than 0, and we will get 0.5 is greater than nu. And nu is greater than, so this is relation we get. Usually nu is equal to 0 means the material can be stretched in one direction with no lateral contraction. That means you can stretch the bar, but in the there will be no shrinking in the other two directions. But usually materials are not like that. So we have this inequality sign. Nu should be greater than 0, and we have that limit 1 by 2 on the right hand side. So Poisson ratio lies between 0 and 1 by 2. What will happen if Poisson ratio reaches 1 by 2? So if you look carefully in this expression, as Poisson ratio reaches 1 by 2, 1 minus 2 nu will approach 0, and once this approaches 0, the numerator will blow up and K will go to infinity. Okay. So when Poisson ratio reaches 1 by 2, K blows up and goes to infinity. That means that change in volume, which is given as minus P by K. So K is a infinite value. That means this numerator, this term will go to 0. That means dilatation goes to 0. That means the material is incompressible. Okay, so when K tends to infinity, the material is perfectly incompressible. Usually water will have a Poisson ratio of 1 by 2. Okay, so this is regarding the dilatation and the bulk modulus and limits on dilatation. That is the bounds, lower bound and upper bound. Lower bound and upper bound for the Poisson ratio. And so we'll solve a very simple problem now, which will involve this concept of dilatation. So we have a steel block here. The length of the block is 100 millimeters, height is 50 millimeters, and width is 75 millimeters. What is given is the material properties are given. Young's modulus 200 gigapascal and Poisson ratio 0.29. So again, Poisson ratio lies between 0 and 0.5. And what is given is the elongation in the, so this steel block is subjected to some compression, that is hydrostatic pressure. So due to the hydrostatic pressure, this block will shrink in volume. So the shrinking in length AB is given as delta AB, which is minus 30 into 10 power minus 3. So what we are asked to find is what is the shrinking in the height, that is delta BC, and what is the shrinking in the width, that is delta BD. So we are asked to find that, and also we are asked to find what is the pressure applied to cause a shrinking. So we are also asked to find what is the pressure which is applied to cause this shrinking. So let's find first what is given. Delta AB is given. Initial length of AB is 1000, so 100. So we can get the strain in the x direction. So strain in x direction is epsilon AB, which is delta AB by AB. So minus 30 into 10 power minus 3 by 100. So 0 will cancel out. 10 you can send to the top. So it will be 10 power minus 4. So minus 3 into 10 power minus 4. Hydrostatic pressure is actually P. So since it is a compressive force, we have the normal stresses sigma x, sigma y, and sigma z as equal to minus P. And for this problem, we have, because the hydrostatic pressure, the strains are also epsilon x, strains are also equal. Epsilon x is equal to epsilon y is equal to epsilon z. Okay, and that value is same as this calculated strain, minus 3 into 10 power minus 4. So we can calculate the shrinking in the height. So delta BC is epsilon y BC. So height is 50, strain is 3 into 10 power minus 4. We get minus 15 by 10 power 3. And the shrinking in the along the width, so epsilon z into BD, BD is 75. So it will be 3 into 75 is 225. So 22.5 into 10 power minus 3. We can calculate the dilatation, which is sum of all those three strains. So 3 into 3 will be 9 into 10 power minus 4. The bulk modulus K, applying the formula E by 3 of 1 minus 2 nu. So nu is 0.29 and E value 200 GPa. So we're getting 158 GPa. So we can get the pressure, hydrostatic pressure, P is equal to E minus EK. So E is minus 9 into 10 power minus 4. So minus and minus will become positive, and you multiply with K. So 158 GPa we are writing as 158 into 10 power 3 megapascal. So if you do the multiplication, you will get 142.2 megapascal. So this is regarding the bulk modulus calculations. This is regarding the hydrostatic pressure and the change in volumes due to hydrostatic pressure. So we have discussed the in today's class. So I'll end the class now, and